All right, this is our first source code example where we're going to see the related assembly. And I tried to create something as simple as humanly possible so that I introduced as few assembly instructions that were new as possible. Unfortunately, we're going to see something this simple is going to actually lead to a decent amount of complexity, which is why I said before that the class starts out a bit complex, but it'll get easier over time. So all we want to do is return from main and return the hard-coded value of hex 41. This will be your compilation instructions in order to actually generate the same assembly. You'll note that it is optimized. We are using the O1 optimization here to try to create a much smaller bit of assembly. And this is what we come up with. We have a single li instruction and a ret assembly instruction. So here's our next two assembly instructions. What do they do? Well, the first one, li, stands for load immediate to register. So it takes an immediate 12-bit, so a signed immediate 12-bit, and it loads it into the register. But a key thing about it is because it's signed, it's going to be sign extended. So if you have, again, 3 Fs, what will be loaded into the register RD is going to either be 8 Fs or 16 Fs, depending on whether you're executing 32 or 64-bit code. So again, just because I say it's RV32I does not mean that you can't use this in 64-bit code. You can, it's just the destination register is going to be 64 bits large instead of 32, and that means consequently the sign extended value is going to be sign extended to 64 instead of 32. So here's a concrete example that is in the actual code that we just compiled. It had li A065. So 65 in decimal, again, GDB disassembly is always going to be showing you stuff in decimal. 65 is the hex 41. So 65 is going to be loaded into A0. So the A0 register will just be all zeros in 65, or all zeros in 41 in hexadecimal. Now by convention, the A0 is not just the argument 0 when passing arguments to functions, but it is also the ABI calling conventions register where return values are stored. So you're returning a value, in this case hex 41, 65 decimal. You're returning the value, and that means it should be placed in A0, which the ABI says is where return values go. Now here's a couple of concrete examples. li, if you had temp 0 and -2, this is okay. This is a valid assembly instruction. Again, it's a 12-bit immediate, and you can encode -2. But this, on the other hand, is not valid. li of 41 into PC, because that destination register needs to be a general purpose register, not the special purpose PC register. And likewise, this li of hex 41, 41, 41, 41 into RA is not possible because you can't encode 41, 41, 41, 41 into 12 bits. Now, I'm a big-time Marvel comic book fan, and I know that most people do not read Marvel comics, but thanks to the MCU, Marvel Cinematic Universe, you are perhaps familiar with a variety of Marvel characters. What is this character right here? Well, that is Scarlet Witch, or Wanda Maximoff, as seen as starting in Avengers 2, but she also, recently had her own series on Disney Plus, WandaVision. And so in the WandaVision TV show, she was distraught over the fact that she, didn't have her children, and so she was searching for alternate reality ways to get access to her children. Well, in the comic books, a similar thing happened in that she basically lost her mind because of the fact that she found out that the children she had thought she had with the robotic vision were actually just figments of her imagination, and the fact that her powers turned out to actually be rewriting reality. So she rewrote reality, gave herself imaginary children, and when she found out they were imaginary children, she basically lost her mind and disassembled the Avengers. Here's an example of her disassembling Hawkeye. Hawkeye also has a series. Anyways, the point is that Scarlet Witch has chaos magic powers, and she has the ability to completely rewrite the reality that you and I see. Now, in this class, we are going to be using this GDB command, GDB set disassembler options, no aliases. And so in a very famous quote, Scarlet Witch said, "No more mutants," where she rewrote reality and got rid of all the mutants except 198 of them. But in this class, we're going to use and invoke her chaos magic powers to say no more aliases, and we're actually going to wipe away instruction aliases, which are those things that hide the real assembly instructions from us behind pseudo-instructions. So let's go ahead and invoke her chaos magic now. So this is what the GDB disassembler shows us to start with, but if we rewrite reality, we will see that actually without aliases, the li is an addi, and the ret is a seizure. So the lie is a lie, it's actually addi. And we've already learned about addi when we were learning about no-op. So li, actually pseudo-instruction, which is doing addi, destination, x0, the hard-coded 0 register, and an immediate. So you're not just loading the immediate into RD, you're adding the immediate to 0 and then placing the result into RD. So pseudo-assembly instruction li is actually addi. We learned about this already, so that's your reminder. It was used for no-op, but basically it's just taking a source, adding it to an immediate, sign extending that immediate before the addition, and putting it in the destination register. Building up our little diagram again, the lie is a lie, it's actually addi. We now know 2 pseudo instructions and 1 real assembly instruction. Going back to this, rewriting reality again, that ret turned into a seizure. So this is going to be our first compressed assembly instruction, which we will denote with our nice little yellow turning into orange, representing the increase in heat caused by the compression of this assembly instruction. So ret's not real, it's another insidious pseudo instruction hiding in plain sight. So that is a seizure, not a ret, but what is a seizure? I'm glad you asked. It is a compressed jump to register. So jump to register, but this small 16-bit form. You can have a jump to register without the 16-bit form, but this is the 16-bit form, making it smaller code. So this is our first exposure to the RISC-V compressed ISA. I'm going to call it RVC. It can actually be RV32C or RV64C, but just to be generic, I'll call it RVC. And again, as we've said multiple times already, the basic point is if you have size optimization, size of the code, you want it small, then you're going to use this compressed assembly instructions to encode things in 16 bits instead of 32 bits. Again, CISC architectures like x86, they have multi-byte encoding, they have variable sized encoding, and so consequently you could have 1, 2, 3, all the way up to 15-byte assembly instructions. That's how they achieve smaller code size. And RISC architectures like ARM and MIPS have completely different 16-bit ISAs. And when I say completely different, I'm making a distinction in that RVC is ultimately going to be mapping back to the RV32I or RV64I. So basically, although they have different encoding, the assembly instructions for compressed RISC-V are supposed to map back to just assembly instructions you already know. Whereas Thumb and MIPS may have completely different assembly instructions that don't map back to anything. So necessarily, because they don't have a lot of space to encode these assembly instructions, they're no longer going to be able to have generality and be able to encode all possible forms of assembly instructions. So in practice, what this means is that they have chosen these registers, S0 through S1, A0 through A5, RA, and SP. You can use those, which these are the X8 to X15, X1, which is RA, and X2, which is SP. These are the only general purpose registers that can be used in compressed assembly instructions. You can't use X3, X4, X5, etc. So restriction now on the possible registers that are used. And we'll teach you all about that later on in the Read the Fun Manual section of this class. But for now, just know that it's a cut down set of possible possible registers. Now, when you're looking at things in the disassembler, you're going to see a prefix of C dot to indicate that it's a compressed form of an instruction. And as I said before, the values are going to map back one-to-one to normal instructions from the non-compressed form. So if you see c.addi, that is going to map back to an addi instruction. If you see c.jr, that's going to map back to a jr instruction. So the key thing is that most of the time you can just kind of ignore the C dot and know, okay, well, they're using 2 bytes instead of 4 bytes. That doesn't really affect like the logic of what it's doing. So most of the time for reading, you can just ignore the C dot. Unfortunately for writing, if you're going to try to write something, then you have to be aware, you have to read the fun manual to figure out, what possible register values. Are there any restrictions? Can it perhaps not use 12-bit immediates? Maybe only use 6-bit immediates or 8-bit immediates, etc. So there are more restrictions on things. You don't care when you see it when you're reading, but if you're writing, you definitely have to care and read the fun manual. So we'll have a couple exceptions very soon where, unfortunately, although things do map back directly to actual RV32I or 64I instructions, they have mnemonics or names that don't map back to the core just one-to-one back to things. So we'll see some, this is why I said this first section gets a little complex. So again, ret's not real, it's a pseudo instruction, and in this case, it was a compressed jump to register RA. So here we have our ret pseudo assembly instruction. It points at a compressed jump to register, but a compressed jump to register implies there is a non-compressed jump to register. So if that's a c.jr, what's a jr? Glad you asked. That's just a jump to register, and that is defined as follows. We have a source register, and that source register is simply set, the PC value is simply set to the source register value. So the specific example used by a ret, so if you have a ret pseudo instruction, it specifically needs to be using RA, the return address register, as its source register. If it was using, x3, x4, x5, x6, those are all possible values for this source register, but that would not be interpreted as a ret by a disassembler. Only when it's using RA, jump to RA, will it be treated as a ret. And again, that's the return address register, which is set to the PC value. So again, it's an ABI convention that RA shall be used as the return address that is stored when you're calling into a function so that you can get back to where you came from. The RA is the return address back to where you came from after the call to a function. But I want to be clear that this RS could actually be any possible register. It's just the RA form which is interpreted as ret. But now we have yet another pretender. These pseudo instructions are popping up everywhere. This is ridiculous, and this is not what I was hoping for when I said, let's make the smallest, simplest possible, just return a hard-coded constant assembly instruction. I didn't want to go through all this complexity. I considered pulling it all out and, treating it in a, separate section, but I decided, you guys can handle it, so let's go ahead and keep trucking here. The JR is a pseudo instruction for a different instruction called $. So I'm going to pronounce $, like dollar, because I have this nice low resolution picture of a dollar store, and I went to all this trouble of creating this slightly italic so that it matches the slightly italic $. So yeah, $. This originally was because I had, when I was learning RISC-V, I misinterpreted JAL, and I thought that was going to be a pseudo instruction for call, and I was like, JAL like call, JAL like call, $, like dollar, JAL call, etc. But yeah, it's pointless at this point because I found out that it was not just JAL as call. Oh well. So $, jump and link register. Jump and link register. What does that do? Well, we have a source, a destination, and an immediate 12-bit. Take the source register, take the value inside of it, take the immediate 12, sign extend it, add them together. Then take that value and place it into the PC register. So that says we're doing a calculation. This is the calculation, and it tells us we should now be jumping to a new location. The program counter is set to a new location. That's going to be the new location of code to execute, because the program counter always holds the next assembly instruction to execute. Now there's one other little minor thing that doesn't just fit nicely in this little math, and that is that there is a side effect of setting the least significant bit of the final address. Take this, calculate a final address, set the least significant bit to 0. This is to try to enforce alignment. So basically, we know that assembly instructions are either encoded in 16 or 32 bits. That's 2 or 4 bytes. That means that all valid assembly instructions should always be a multiple of 2. So every compressed assembly instruction is going to end on an address 0 or 2 or 4 or 6, and your non-compressed ones are 0, 4, 8, 12, etc. But by setting the least significant bit to 0, that just enforces that every single possible value placed into PC is going to be a multiple of 2. And so that is to try to avoid instruction misalignment. Now there is a secondary effect. This is jump, and that is the jump, but end link register. What is the end link register? So this RD, the R destination, you can see we didn't calculate something and put it into a destination register. The destination for the calculation is PC. So what is RD? RD is going to be the address after the $. Instruction, aka whatever, the program counter was pointing here and it said, hey, execute this $. So program counter was pointing there. The address after that, assuming that we're using non-compressed things, is going to be that plus 4. So basically, at the time that this was executing, the PC plus 4 is the next assembly instruction right after it, And so take that PC plus 4, the instruction, the address after the instruction, and place that into the destination register. So this is basically going to be, again, like a link register. This is our way to get back. If the JALR is calling into some function or returning back from a function, the destination could be the way to get back to where you came from. So when it's used for a call, you would want to do that, but if it's used for a ret, as is the path that we're currently hunting down, then that would have no point whatsoever. So again, the link register, this destination of the JALR, that's how you get back to where you come from, but you may or may not want it. So we said right now we're doing, ret is compressed JR, so ret is compressed JR, JR is actually a JALR. And so if ret is compressed JR RA for return address, and JALR is actually the X0 register is used for the destination, and RA is used for the source. So RA, which is where we came from before main was called, RA, the return address, plus 0, and so place that into PC. So just go back to the return address, and then store into the link register the address after the JALR, but this is a ret. We don't want to come back to after the ret, so just store it into X0 and it'll basically be thrown away because X0 is always hard-coded to 0. You can store anything you want there, but it's not going to have any effect. X0 shall always be X0, shall always be the hard-coded value 0, rather. So again, what's special about ret is that it's using the RA, and per the ABI calling convention, RA is the return address where it can return back to, RA return address. So here is our summary of what we learned here. Super simple code. All it's doing is returning hex 41. We start out with these pseudo instructions, li and ret. Those are sort of the nice form of things. Those are perhaps easier for humans to remember sometimes. Li, load immediate, so it's just loading immediate 65 into A0. That's easy to understand. Ret, just return back, return to the return address. It's hard-coded. It doesn't even bother showing you the return address. Just return back to whatever the return address is. Set the PC to whatever the return address is. So the lie is a lie, though, and the ret's not real. These are both pseudo-assembly instructions. And the real assembly instructions behind the scenes that were actually used for this compilation, for these compile options, is addi, where we have 65 added to 0. So here's the long form. Here's the extended form in English, right? Addi, we have the value 65, which is hex 41, plus 0, the 0 register. Add those two together and place it into the A0 register. And the special reason why it's choosing to use A0 is that per the ABI calling convention, A0 holds the return value at the time a function returns. So the original source code, 41 shall be returned back out of main. So when it returns back out of main, 41 better be in the return value. The return value is the A0 register. So then c.jr RA is jump to the address stored in RA, which is a special address per the ABI calling convention. It holds the address after the address of the function that called this function. And what is this function? It's main. So someone somewhere called main, and they placed the way to get back out of main. When you return back out of main, they placed that value into the RA because they're abiding by the ABI calling convention. So basically, it's going to return back to the RA value. It's going to jump to the RA value, set the PC to the RA value, but also don't bother with storing the address after this instruction. Don't do the linkage because we don't need to come back here. It is a jump register with RA, but jump register specifically doesn't link anything. So it's a pseudo instruction jump register for JALR, which is jump and link register, but specifically use JR when you don't want to bother linking. You are just going to set the link register to the 0 register so it doesn't bother storing the address afterwards because we're never coming back here again. Okay, with that, we picked up another assembly instruction, JALR. And building up from here, we had our c.jr pointed at JR. This is a pseudo assembly instruction, though we found out. It turns out that JR is actually JALR behind the scenes. And then the only thing I want to say here is that if you were compiling without compressed instructions enabled, then your ret would probably use a JR or JALR instead. So ret could actually be a JR, not a compressed JR. It just depends on whether or not something is being compiled with compressed instruction support or not.